So the autoionization of water was discussed last year. Water can react with itself and autoionize. So you're going to get a hydronium ion, which is that H3O plus, and you can get a hydroxide ion from water. Okay? And this always happens. There's no way to prevent it. So, okay? That was presented last year. Now we can dive into the math and the fact that it's an equilibrium and quantify it way more than last year. We can write an equilibrium law expression now from this reaction that was introduced last year. So the top would have concentration of hydronium, H3O plus, in aqueous solution, concentration of hydroxide in aqueous solution, both to the first power. On the bottom, we would have, you wouldn't have pure substances. Water is really the only one I presented earlier. So this is liquid water in an aqueous environment. The reason it's being dropped is because the water doesn't change. Okay? So in this equilibrium, the amount of H2O molecules changing in my glass of water is trivial. It's irrelevant. It's really a constant. Okay? And that concentration of water is pre-built in the KC. Okay? Now this equilibrium is so important, so fundamental to biological life, it gets its own constant. You know you're special when you get your own constant, and that's referred to KW. Question? And that is given right into your data booklet. So it's not even a number you have to memorize. So KW is 1.00 times 10 to the minus 14. As a reminder of how to enter this into your calculator, I really encourage you to not do 1 times 10, use the little up arrow for the power. Okay? That does work, but you can get into an order of operations problem when you do it that way. Okay? The best way to, if you have I think most probably have a TI version of a graphing calculator here, and you're going to enter the front number 1. Okay? With your calculator, it actually does not matter if you put in 1.00. It's going to drop them anyway. Calculators don't do sig fig. So 1, you have to go second, and then the button says EE, but it only puts 1 E on your computer screen. And then you put in the power. Okay? And that will represent 1 times 10 to the power of minus 14. The green piece is what the E means, because it's just because it doesn't have the ability to put those characters into your screen. So now I can explain the pH scale a lot better than I could last year in Chem 20. Okay? If we look at a neutral pH, last year I kind of have to lie. I'm teaching Science 10s, and it pains me to kind of lie to them. But you basically say, you know, an acid, if a solution is neutral, it has no acid and no base. And it's kind of true, but the real truth is, at a neutral pH, it's not an absence of, it's a tie. The concentration of hydronium equals the concentration of hydroxide of something that's neutral. Okay? There is a little bit of both. Okay? And we can solve for that exact value. Okay? KW is a constant, 1 times 10 to the minus 14 at SATP, so standard conditions, and we're going to do all our calculations standard. We're going to solve for what would this be? Okay, well this and this would be the same, and I'll use every teacher's favorite variable, which is X. So instead of hydronium, I'm going to put an X. Now, the hydroxide has to be the same, so that's going to be another X. They have to be the same value, and that's going to equal 1.00 times 10 to the minus 14. And this statement's only true if it's neutral, and that's when X and when hydronium and hydroxide equal each other. So X squared equals 1.00 times 10 to the minus 14. I want to solve X, which is my hydronium or my hydroxide. and x equals 1.00 times 10 to the minus 7. I didn't have any units in, but same as before, whenever we used equilibrium constants, the concentrations outputted our moles per liter. So our hydronium under this neutral scenario is 1.00 times 10 to the minus 7 moles per liter. If you solve for the pH of that, which we'll recap shortly, so I didn't show my work, that's where the 7 comes from of a neutral pH. So no scientist made up this number. No one in their right mind would pick 7 as the middle value if you're making up a scale. Okay. But it wasn't picked. It's due to the equilibrium value. So this 7, that 14 sets all your values in your pH scale. Okay. So let's recap all those calculations. This is a day where hopefully I maybe bore you a bit, but we got to pull back all that Chem 20 material. And then you're going to be practicing those calculations this morning, and then we'll make a jump forward into Chem 30, the second half of this class. Okay, so you need to be familiar with all of these formulas. So the concentrations that were mentioned already can be expressed in pH and pOH. That's what my parents, the news, everyday world likes to use. Okay? My parents do not get scientific notation. It's just not something they use. But they get the pH scale. You know, they know low pHs are acids and high pHs are bases. So you got two similar equations. The power of formula is the negative log of the concentration. If you want to undo the pH, it's 10 to the negative pH. Send you back to concentration. Same with the base. And we have the two power ofs, the power of hydrogen and the power of hydroxide, sum up to 14. And again, that's directly due to that power in the kW value. That was Chem 20. We now have one extra tool. kW is hydronium times hydroxide. This wasn't in your toolbox last year. Wouldn't have made any sense to you last year. So I've laid out the 4 possible variables in a square. I just want to remind you how to go from one to the other and the fact you can't do any diagonals. So if you try to do a diagonal, you've got to do 2 steps to get there. So how can I get from hydronium to hydroxide, which, yeah, we're going to have to use this blue guy to go, and you'd rearrange it depending on which way you're going. So we would have to use this, and we could go either way. So what about from hydronium to pH or pH vice versa? We basically just need to find the formulas of those 2 pieces, and that's those 2. So depending which way you're going to use one of those 2. These 2, hydroxide, pOH, we'll let you go back and forth there. And last, the fact that they sum up to 14 lets you go pH to pOH. Okay. So last year, you couldn't do this top one. If I gave you hydronium, you kind of go all the way around, and now you don't. When you're solving problems, if you're trying to do a diagonal, you've got 2 options. You're trying to go, if I ask you what's the pOH and they give you the hydronium, you could go this way and down or that way and down. So if you're working with somebody, you might get to the same answer and have gone a different way around. Okay. Now you may not copy this down. You certainly did this last year. Just a quick recap of the pH scale, getting it fresh in your mind. Okay. So You can put a number line in your notes or not. Don't worry about memorizing any of these compounds. Just reminding you, 7 is your neutral regardless of the scale. The pH is on the top. The pOH is on the bottom. And we're seeing how they always sum to 14. If you look at any of the top and bottom, 10 and 4 is 14, 11 and 3 is 14, 14 and 0 is 14. Okay? And I really emphasize to my students this arrow going right off the chart. Okay? I come across, particularly grade 10s, you think, the pH scale is 0 to 14. That's it. You can't go below 0. Yes, you can go below 0. You can go to -1 on the pH scale. And here, you'd be at 15. They still sum to 14. Now, it gets hard to go off the pH scale because you have limits of how many moles you can jam in 1 liter. So pH of -2 is almost impossible to get to, 1.5. Sulfuric acid is about 1.5 when it's concentrated. Okay? You can't jam 10 moles of something into 1 liter in most cases. So that's why it's most commonly 0 to 14 is the really common numbers. So I'm going to just do a few examples, kind of like Chem 20, and then we'll roll into Chem 30 more in the second half. In solving questions, there's really 2 distinctive cases that require vastly different strategies. Okay. You can have a strong acid or a strong base, and they're going to react 100%. We're going to review them today. You should be familiar with them, but that was the heart of Chem 20, the 100% reactions. And in stoichiometry in Chem 20, all you did was 100%. The whole course is really based on no equilibrium. All that's left for this year. Weak acids and bases, which ionize less than 100%, these are our equilibrium, and this is the big focus of Chem 30. And you couldn't do it last year. These you need K values to solve. Again, for acids and bases, you're going to need a Ka value for an acid, or you're going to need a Kb value to solve questions with bases. Now, we've got a few more skills to go before we really dive into these. So I'm going to do a couple examples. You're going to practice Chem 20. Or you can do these, but we're going to do them with a percentage today before we move into the K values. So I'll leave uncovered. I've laid out a nice table underneath. Determine the hydronium, hydroxide, pH, pOH, so all 4 of those variables for about 1/4 mole per liter hydrobromic solution. Now, I told you in this opening question that it's hydrobromic, that hydrobromic is strong. That information is going to be totally removed from this course. You have to figure that out in questions, but your table is your guide. You've got these are some strong acids that are written right on the table. You know they're strong because their K values are infinitely large, or the table just says very large. So these are your strong guys, and there's a few more that you have to know other than the ones that are here. And I'll recap those in a future lesson. Okay. Hydrobromic is right on your table. Okay. Our weak species are all of these middle ones between the gray lines. Okay. So anything you see here, HF, you would know it's weak for sure. It's got a K value, and it's in this middle section. Okay. So this reaction is actually going to be 100%. The best arrow would have been just a forward one. It's not going to go backwards. So if we look at how much hydrobromic acid we start with, it's all going to go away. I left my per liter out of the top units when I first wrote them. All of that hydrobromic acid, this change is going to 100% tell us our change for H3O plus is going to start at 0. 1 HBr is going to make 1 water. And all strong acids have this 1-to-1 ratio. So you're going to make almost a quarter of a mole per liter. When I'm doing this once, okay, you don't really need a nice table. You don't have to write this red bit down. With a strong acid, all of the acid initially is going to turn into hydronium. So you really should be skipping all of this, but I'm just reminding you of this. I didn't want to jump right into skipping it, but you know, you're just going, the hydronium is just that number because it's strong. So you'd have to, you know, verify it's strong. This just works for acids. Bases have a slight extra twist. And now I can really just recap all those mathematical calculations. I'm going to write those out fairly quickly. Okay. The first one took brain power, but not calculation power. Hydronium is the same concentration the acid started with. There is 0 HBr left at the end. None of the H's and the Br's are connected. 100% of them came apart. I'm going to choose to do pH next. Okay. Again, I could have went to hydroxide next if I wanted to, and then Kw is hydronium times hydroxide. But I'm going to do pH. That's the negative log of the hydronium concentration. And when I do that, I get 0.607. Okay. I'm going to remind you of your sig figs for when you go to the power of. This isn't a multiply, divide, add, subtract. So none of those regular sig fig rules apply. There's different ones. The amount of significant figures in our normal number is how many decimals we have in a power of. Doesn't matter, pH in this case. So there are 3 significant figures, so it's going to turn into 3 decimal places. Any numbers in front of that decimal don't count. The numbers in front of the decimal are more coming from the power part of the, if we express the concentration of power. So that's pH, pOH, okay, is 14 minus pH. So I've rearranged that formula. Again, I'm trying to do this quick because this is a repeat. It's a recap lesson. Okay. Treat this as 14.0000 for your calculations. Just keep the same sig figs, the decimal places, or whatever you inputted from the pH. So when you do that, I get 13.393. Okay. And this is where I really want to highlight, if we do something with this number, we just treat it as having 3 significant digits from the 3 decimal places. When we switch the power of, the numbers in front, you might go from no numbers to 2 numbers, but that doesn't matter. Last, I'll get hydroxide concentration. I can get that from 10 to the negative pOH. So that'd be 10 to the negative 13.393. And this is where I'll highlight the sig figs again. We're going to do it the opposite way now. 3 decimal places in the power of means 3 sig figs when we go back to a regular number, not a power of number. So my 3 sig figs are 4.05, and it's times 10 to the negative, and then I wrote messy. So I was going to do this second one. I'm curious to see how far you can get yourself. I'm going to highlight the few twists, okay, and then see if you can get through the math. So it's determine all the concentration, all the 4 possible ways to output, acid-base type problems, hydronium, hydroxide, pH, pOH, but I'm not going to give you the concentration. I'm giving you 1 gram made up in a quarter of a liter. Now this is a strong base. Okay. Now the solubility of magnesium hydroxide isn't huge, but ignore the solubility piece. Assume 100% of this dissociates. See if you can figure out the hydroxide, the hydronium, the pH, the pOH. Now you're going to have to solve for concentration, moles over volume. Okay. You're going to have to go mass to mole, divide by its volume. So that you did a lot in Chem 20. That's not the real twist. What you have to watch out for is that when you solve for the concentration, you are solving for magnesium hydroxide's concentration. How does that compare to the hydroxide concentration? It's not the same. With the acids, they're all 1-to-1. So when you get the acid concentration, it all turned into hydroxide. With the bases, you have to watch out. What do you get? Double the hydroxide compared to the 1 unit of magnesium hydroxide. So when you solve for this concentration, this is MgOH2. When it comes apart, you've got to double it. And then all the math is fairly similar to what I did already. Full minutes. We're going to determine the pH and the pOH for a ammonia solution, okay, which is a weak base. Now in the future, we'll learn how to somehow use this K value and find ammonia, okay, but we're not ready to do that strategy yet. So we're going to solve this with a percentage, okay, and then we'll leave this strategy behind in the future, okay. Anytime something is weak, you need a nice table, you need to set up an expression, okay? All of this ammonia is not going to turn into hydroxide. Okay? How much of it? Well, 2.1% of it is what's going to turn into hydroxide. And that's what I want to lay out in a nice table. So our base, our weak base is ammonia. When we put it in water, it's going to react with water. But not completely. We're going to get an equilibrium system, which is what we're learning about in this unit. Okay. The base will pick up an H from water, an H+. And we're going to get ammonium, and what's left over from water is hydroxide. And that's why it's a base. And we're going to spend a whole many days, we're going to start learning skills of writing equations like this in part 2 of today. So if you're not fully sure of how I got this out, I will teach, you will learn it. So we have 0.0875 moles per liter of ammonia at the end. It's not going to 0. Only a little bit is going to get used up. I'm going to have to figure out what is that little bit of ammonia that does react. Well, of all of the ammonia, (2.1% react. How you take a percentage is the same, whether you go to a store and you're paying 5% GST, or you're doing science. What do? You turn the percentage into what? Into a fraction or its decimal form, and multiply. So 2.1 divided by 100 is that fraction form, which would turn it into a decimal if you did that division. Okay? So 2.1% of all of that base is 0.00184. So that is the amount of ammonia that's going to react. Not very much, 2% of it. That also tells us, once we know the amount that reacts, now we can do our stoic and predict how much hydroxide. All of our weak equilibrium reactions are always going to be 1 to 1 to 1 to 1, which makes the math actually quite simple for our calculations in this unit. If you set it up right, the math is going to be the easy part. The math will be a little harder in those early KC type questions because they're not all 1 to 1 to 1 to 1, but it's always one acid or base. We'll see one water, one, we'll call that a conjugate starting later today, and you get one of the acid or the base. So it'll always be a multiply by 1, divide by 1. So start with 0, and there, that 2.1% of the original base turned into hydroxide. This question I wanted pH and pOH was my two questions. I'll just write a statement. This wasn't actually one of the questions. I can get the pOH first. So 10 to the negative log of that concentration will give me pOH. I have 3 sig figs, so I should have 3 decimal places. 2.736. And I'm just making the sig figs blue. Okay. We don't consider this first digit in front of the decimal of sig fig. And last pH, 14 minus that, so 11.264. Again, I'm maintaining those 3 decimal places, so there's 3 sig figs. So that's our intro to acid-base calculations, pH, pOH, and a super fast run through the pH scale. And we now know why 7 is the middle value. So I'll give you a bit of time to practice, and then we'll move into conjugate acid bases, Bronsted-Lowry theory. Arrhenius theory is what you used in Science 10 and Chem 20. Bronsted-Lowry is your grade 12 theory. And then in post-secondary, you may move into Lewis